Hey, welcome to The Art of Code. My name is Martijn, and what you see behind me here is an easing or tweening function for a bounce that we made in the last video. Easing functions, if you have never heard of them, they are used in many different places where you have animation inside of software. So inside of video games, inside of any UI program that uses animation, also inside of video editing software, 3D software, easing functions are used throughout. And most of the time, you can just take one off the shelf and use it. But what I like to do is really go deep into it and figure out how things work and play around with it so that we can figure out something new maybe, or get creative. And so in the last video we made, I showed two different ways how you can make this bounce. And as I was playing around with it, I was like, well, we can probably do this in a smarter way. So that's what this video is about. And we're going to use logarithms to do this. Logarithms are a bit mysterious. Everyone has them at some point in high school, but I think if you're anything like me, then that's already long gone, and you don't really think about them anymore. But if you are into computers, programming at all, then it's good to know about them, and it's good to be able to play with them and have some intuition of how they work. So this new bouncing function is going to use that. So if that interests you, stick around. All right, so here is where we left off the last time. So this is, if you're new, that's not a problem at all. You could follow along right away. There's a link in the description, and you will open up ShaderToy in your browser, and you can just follow along. No problem. Okay, so this is where we were last time, where we had this bouncing function, and it's pretty cool, but there is perhaps a problem. Because it uses a for loop, and for loops are kind of expensive. So now actually, before I say that, computers these days are incredibly powerful, and if you just do a for loop once for something, then and you're not working for Google or some company that needs every last electron in the computer to do actual useful work, then you can probably use a for loop just fine. But just as a mathematical fun exercise, let's try to do this without a for loop, because we could run out of bounces. Let's say if we had like many bounces, then at some point we're just going to run out, and it's just not as elegant perhaps as it could be. So let's try to do this differently. So what we want is a function that kind of can divide up a space into the first half, and then the remainder, chop that up into half, and then the remainder of that, chop that into half, and each time, so all the way. And there is a function that can do that, and the function is a logarithmic function. So let's have a look at that. So let me just go over here, and let's look at the log base 2, and for that I'm going to have to go over here. Because I don't know how to do subscript inside of Desmos. Oh, this is Desmos, by the way, if you don't know. Desmos is also a website you can just follow along. It's a really cool graphing calculator. So if you want to figure things out about functions, or play around with functions, or get an intuition for functions, then Desmos is definitely a great tool to play around with. All right, so I'm going to do the log base 2 of x. And what does that mean, a logarithm base 2 of x? Well, a logarithm is basically the same way as how subtraction is to undo an addition and division is to undo a multiplication. Well, a logarithm undoes an exponentiation. And so what this does, this gives me the answer. This says, to what power do I need to raise 2 in order to get x? Okay, and if that doesn't make sense, let's do some numbers. So let's say, to what power do I need to raise the base 2 in order to get 2 as an answer? Well, then you look at this graph and you look at 2 and you go up and you see, okay, it's 1, right? It's at a height of 1, because 2 to the power of 1 equals 2, okay? Similar, to what power do I have to raise 2 in order to get 4? Okay, well, I go up and I see it's 2, because 2 to the power of 2 equals 4. Okay. Similarly, in the range of 0 to 1, let's have a look at it. Let's have a look at 1. So, to what power do I have to raise the number 2 in order to get 1? And the answer is 0, because 2 to the power of 0 equals 1. Any number to the power of 0 equals 1. And so, but look at what happens inside of here. So let me just make a line here at 1/2. To what power do I need to raise the number 2 in order to get 1/2? And the answer is -1. Because 2 to the power of -1, and if you do a negative exponent, that's 1 divided by that exponent. So this is 1 divided by 2 to the power of 1, basically, which is 1/2. And so every time I halve this, here, let me just go from here to here. Every time I halve this, so now I'm at 1/2, right? At 1/2, it points to -1. At half of that, at 0.25, it points to -2. At half of that, it points to -3, and so on and so forth, all the way to infinity. And we can use this. So let's try to use this. So let's go over here, and let's go down here into the main image function, and let's visualize the logarithm of x, log base 2 of x. And actually, let's only do it on the bottom of the screen, so only when uv.y equals or smaller than 0. And then we take the log base 2 of x. And do we have x? Yeah, we have x. So let's see what that looks like. Okay, so that seems like it didn't work, but this line here disappeared, and that gives us a clue that this got all filled in with black. And the reason why is because I'm looking at this between 0 and 1, and between 0 and 1 this is smaller than 0, and smaller than 0 gives you a black screen if you convert it to colors. So, well, that's simple enough. We could just turn it around, right? We could just put a negative here, and then we have it positive. So let's do that. So I put a negative here, and then we have it positive. And now here it's black because it's 0, and then it goes all the way to 1. 1 is somewhere over here, and then it's just white after that, because in shaders, anything below 0 is black, and everything above 1 is white. And so that's why it's white over here, and we can't really see what's going on. But what we can do is we can just take the fractional component of this number by taking the fract over here. So that just, not artifact, fract. So that just splits up the domain, or basically it discards the integer and it just keeps the decimals. And so now we have something like this, which you can see how that can be useful already. If we can draw a parabola inside of each of these, then maybe we could make something. So yeah, so let's just turn this around because we want the big bounces to be on the left, right? Well, we can just do 1 minus this, and then it turns it around. So let's use this to draw some parabolas. So I'm going to make a bounce 3 function. So over here was my bounce 2. That's old news now. Now we can make a bounce 3. So bounce 3 takes as an input a float x and a float r. And inside of here, I'm going to do, I'm going to take this. Okay, I'm going to say x equals that. And then I basically have what I see over here, and now I can draw a parabola in that. So these numbers are like wherever it's black, the number is 0, and wherever it's white, the number is 1, and between it goes between. So we're just looking at a number that goes from 0 to 1, 0, 1, 0, 1, right? And so similar to how we drew a parabola in the previous episode, we can just like do something like this. We're going to say x minus 0 times x minus 1, not and, times. Okay, and that gives me a parabola between 0 and 1. So we don't need to do x minus 0, we can just do x. Right, so that gives me a parabola, and then I can turn it around. And now between 0 and 1, I have a little bounce. Okay, so Let's do that. Okay, so I can just say over here, I can say float bounce equals x times x minus 1, let's say, and let's return that. So return bounce, and then I have to obviously look at it. So this is my old bounce, my bounce 2. That's old news. We're going to do bounce 3 now. Okay, there's my bounce 3. Well, that's negative, but that's simple enough. We can just turn it around by putting a negative there. Okay, well, that's pretty cool. So let's see if we can't change the size of these bounces. And the way to do that is if I go back here to the logarithm. Actually, let me take the so over here, I'm taking the fractional component of that, right? I can do the same thing over here. Although over here it's called modulo, mod. Fractional is just a mod 1. It's basically just throwing out all the integers and just basically cutting up the graph and at every integer interval and just shifting all the parts of the graph back down to 0, so that we have all these parts of the graph right now. And we're only looking at this, by the way, on the interval of 0 to 1. So this is my x coordinate basically, and we can change the distribution of this by changing the base. So now it's a base 2, but I can just make it a base r, let's say. I screwed it up. Okay, here, a base r, and then I have to make r, and r can go from 1 to whatever, to 10, let's say. And now I can change this, you see. So let's do that over here. So what I can do, well, inside of here I don't have an arbitrary base logarithm. But in order to get an arbitrary base logarithm, you can just divide. Well, I can take the natural logarithm and then divide it by the log of the base that I want it to be in, and that converts it to that base. So now I have bounces that I can move around, which is pretty cool. And let me just hide this because this is not in sync right now with what I'm doing. Okay, so now I have that. Now the next thing I want to do is I want to make these successive bounces smaller, right? Like each bounce needs to get less high than the previous one. And for that, I can just multiply this bounce. If I multiply this by, let's say, 0.5, then all bounces are only half as high. But I want to change it per bounce, right? And so before I do that, I have to first figure out which bounce I'm in, which bounce I'm part of. And to do that, I'm going to just take this. Let me just take this and cut this out and call this x and put that over there. So that didn't change anything, right? That's the same thing. So this is just cutting up the domain, right? And this is like over here, I still have the original function, right? So I still have, well, I'm not going to do it here, but the original function that was, well, yeah, let me just log the log of x basically, and then minus that, right? So here I have the original function, and then over here I kind of chop it up and I move all the parts. But what I can do here before I chop it up, I can figure out where between which two integers am I. And to do that, I can just say float I is the floor of x, and that gives me for the first one 0, and then 1, 2, 3, 4, whatever. And so now what I can do is I could do a few different things. I could like divide it by that, let's say. And then I have to get rid of that. Yeah, I could divide it, or what I could do is I could multiply it by the power by the base, which is the length of the bounce, which is, let's say, 1/2, raised to some power. Because if you have a 1/2, well, 1/2 to the 0 is 1, 1/2 to the 1 is 1/2, 1/2 to the 2 is 1/2 times 1/2, so then each time it gets smaller, successively smaller. And so here I have to actually divide it. Okay, so now it gets smaller, smaller, smaller. Which is pretty cool. Let me also make this at 1 height. So I multiplied it by 4, and then over here, if you saw my previous videos, I just, in order to get it in the nice range, I just multiplied by 0.4. So I just put that over there. Okay, so now we have cool looking bounces. Oh yeah, okay, so now one thing here is that the bounce gets higher. That is because we probably have to add 1 to this. Yeah, now the first bounce just always stays at the same height over there. All right, now one thing that you might have noticed here is if I skew this too much, then you see that the bounce is actually not a proper parabola. And that is because if you go to Desmos, you see that my x-coordinate here that I'm using, that you can see over here, it's not straight. It's actually because it's just part of the original function cut up and put down, and so my x-coordinate is kind of bent right now, and so what I have to do is I have to unbend that. And so let's try to unbend it. And I said before that exponentiation and logarithms are the opposite side of the coin, right? One undoes the other. And so in order to undo this, what I have to do here is I have to take r. Let me see here. I have to take r and raise it to the power of x, and actually minus x, because I have a minus over here. So I have to put a minus x. Okay, so now I have something that is a straight line. Okay, now it's upside down, inside out, whatever have you, but we can fix that. So so let's just try to do this. Actually, before I do this, because over here the situation is a little bit different than I have over here, because over here the big bounces are on the left and it gets successively smaller towards the right, whereas over here I have it the other way around, and that's because I haven't turned it around over here yet. So let me just turn that around so that we're looking at the same thing. All right, so now I have this. Now I have to just make this match the blue line. So how can I do that? Well, the first thing I can do is I can throw it upside down, right? Just do 1 minus. And now I just have to scale this up so that it fits. And yeah, I don't really know what the relationship here is, but what I can do is I can put this to somewhere where it makes sense, right? So if I set this to 2, then it comes to 1/2 height. Okay, so now if I would take this entire thing and I would divide it by the inverse of this, right, by 1 divided by r, right? So if I divide this by 1 divided by r, then I have what I need. The only thing is that if I move it, it doesn't work. Okay, so for 2 it works, but it doesn't work for anything else. So let's look at one other number to see if we can't figure out what this is. So at 2, it's 1/2. Okay, at 3, let's see where we're at with 3. 3. So at 3 it comes to here. That's 2/3. That's already something, right? So at 3 it is 2/3. Okay, that's interesting. At 3 it's 2/3. At 4 it is 3/4. Okay, so now a pattern is starting to emerge. So let's see here. Let's divide this. Not by, in the case of 2, right? So in the case of 2, I just divided it by 1 divided by r. So I have 1 divided by r. But for 3, I need not 1/3, I need 2/3. And for 4, I need not 1/4, but 3/4. And so what that turns out to be is 1 minus that, right? Because at at 2, I have 1 minus 1 over 2, which is 1 over 2. At 3, I have 1 minus 1 over 3, which is 2/3. And at 4, I have 1 minus 1/4 is 3/4. So now I have something, I created something that undoes the distortion properly. Okay, so now if I go back here, and let's go somewhere where there is distortion, like over here, now I can go over here and I can say x equals 1 minus the power of the base. Let's just call this base actually over here because that makes more sense perhaps. It's the base of the logarithm. So let me just change that. And then over here as well. And then over here I'm going to say 1 minus the, what was that? The power of 1 minus the base, but we already turned that around. Oh no, we're over here. 1 minus and then the base minus x. Okay, so 1 minus the base to minus x. Okay, and then I divide that by, what do we have? 1 minus 1 over the base. Okay, that should probably be it. So let's see. Booyah! So now we have the distortion undone. How cool is that? All right, cool. So now we have only one thing left, which is to move the first bounce so that it starts at the top and not at the bottom. And the best way to do that is to go over here and say x minus equals. So here we could like move this around, right? Move, like shift this. The question is, how much do we have to shift it? And like at first I thought, well, 0.5, right? And 0.5 almost works, but not really. And it turns out it's the same issue as what we just fixed over here, is that we need to account for the fact that we did a logarithm. So what I'm going to do here is I'm going to copy this. I'm going to put that over there. And then instead of x, I'm going to put 0.5 into it. No, minus 0.5. Perfect. All right, and now I have a bounce that starts at the top. Pretty cool. So let's see here. Okay. So now this is much better than the previous version because now we don't have a loop and we have infinite bounces if we wanted to, as many as we want. How cool is that? For the same price. So yeah, so that is pretty cool. Now one more thing, you could play around with the height of the bounce here. So we could make this smaller here to get smaller successive bounces. So that's something that maybe you would want to expose. So now this is obviously like very advanced, very complicated for a tweening function if you just wanted to move something in a UI or whatever. But I think it's fun to play with these things and to try to figure out, how to do things. Like it took me a while to figure out how to undo the distortion, for instance. But if you play with it for long enough, then you can figure it out, and it opens up things for you. So yeah, one cool thing with this is that you in a video game, let's say, you could. So normally, how you would like, if you're like a video game character and you're like throwing a ball, let's say, well, normally the way they would simulate that is by putting forces on it and then doing a time step each time, right? Like for every frame you just update the ball, whatever, which is fine. But one advantage of this is that you can play with time. You can make it go forward or backward or stop, freeze, do whatever you want. You could make a particle system with 1 million particles that all bounce in certain ways, and it calculates things very, very, very quickly. So yeah, so that's pretty cool. Actually, I'll show one more thing here that I was kind of playing around with. I was thinking, what happens if I could turn every other bounce upside down. Okay, and so let's do that real quick here. So how do I find every other bounce? Well, I can use this I value for that, because this I value goes from 0, 1, 2, 3, 4, 5. And so I know that if this is odd, I know that I need to turn it around. Or I can turn out all the evens or whatever. And so what I can do, and then so when I have it, I would just turn it around, right? I would just do that. So what I can do here is I can take the modulo of I with 2. So the modulo of I with 2 is going to go 0, 1, 0, 1, 0, 1. And then I multiply that by 2, so now it goes 0, 2, 0, 2, 0, 2. Now I subtract 1. Now it's minus 1, 1. And now I can just multiply that by the bounce. Bounce times equals that. And now I get something like that, which is pretty cool. Okay, so now actually what I do have to change this. Yeah, I have to take this out, otherwise it doesn't fit properly. So anyways, this is just something that I just came up with quickly that might be useful for something else. So yeah, that kind of shows you that playing with things that's how you get good at stuff, and how you find new things, you know. So yeah, using tools like ShaderToy or using tools like Desmo is definitely highly recommended for any computer programmer. So yeah, okay, so that's that. But let me just, because this entire video wasn't about this, but it was about this. So let's just keep it like that, and let's make the time go a little bit slower. Let's say like that. And yeah, that's it. So let me know what you think in the comments below. Let me know what cool things you want to see next. Let me know what you can make with logarithms. Logarithms are really it's kind of a mysterious world that I think a lot of people like know very well. You know, like addition, multiplication, division, basic algebra, taking derivatives and stuff like that. But logarithms are often kind of overlooked, and they kind of show a different angle like from which you can approach a problem, you know, like in this case here. So anyways, I hope you like this, and yeah, I hope you stay awesome, and I hope to see you next time.